Okay. Okay, so the last class we have studied behavior of flip-flop. So today I have taken little different slide to convey the same concept. So we have a flip-flop which is D-type flip-flop. Whatever the input is available, after some time that input becomes available at the output. And the timing diagram is as follows. We have a clock here, the clock signal. Okay, and then the transition happens only at the rising edge. And then we have before before the rising edge or positive edge, the signal, that is signal D or input D, has to be stable for some time, right? Or we call it setup time. Okay, this is the setup time. And then once the clock edge happens, after that this input must again be kept stable, right? So basically there is some setup time. So setup time is before the positive edge, and after the positive edge we have to hold it, right, for certain time. Okay, all right. So the whole time is here. That this is whole time. So between this and this is the whole time. Okay, and then from the edge, when clock edge happens, the signal takes some time, or D takes some time to appear at output Q, and we call it click to Q delay. And this, so basically the setup time is required because inputs usually at flip-flop are not stable, and the example is shown here. The next slide. You can see that there is adder here, or we can say it's a kind of ALU or adder, anything you can consider here. There is input Xi, and there is input Si minus 1. So this input becomes here Si minus 1. Okay. Now, so for the output will be available, when both output is available, whether there Si1 is there or not. Okay. So there may be timing mismatch between when Xi is available and when Si minus 1 is available. Okay. So let's assume that there is a little delay in Si minus 1 to happen or to appear here. Okay, and Xi is available. The output here will be addition of the two. This could be 0 or whatever, or previous value of Si minus 1, right? And so signal here may not be stable for some time, right? That's the reason we have this, this part as undefined or unknown signal, because Si may not be having correct value, but after some time, if the circuit design is proper, then after some time at the leading edge of the clock, this signal becomes stable. Okay, all right. So this diagram explains why we need, why there is a setup time required, and then similarly there is a this expression for hold time. All right, because it takes some time for register to accept the input that's available. Although we say instantaneous, but takes, so this signal need to be remained. The input D or input that is coming, both inputs that's coming to register, or a single input to register, should remain stable for some time. Okay, after leading edge of the clock. Okay, so that's the reason we have these two periods, that is setup time and hold time. Okay, so with this knowledge, let's go ahead. And then we have also discussed about critical path. Okay, critical path is kind of path which is the longest path, right? Which takes the longest delay between the two registers, right? Here we have normally we yesterday we discussed about a critical path for a sequential circuit, which is shown here. Okay, but critical path, but in microprocessor we have combination logic circuit between two registers. Okay. So for example, you have you take data from register, then it goes to ALU, it does some addition, and then it goes back to register. So we can consider that there are two registers. So the critical path here is obviously something that goes from this register to first CL, second combinational logic circuit, then this header, and then finally to output. So critical path delay for us will be click to queue delay, okay, which could be corresponding to, we can either take this one. So let's assume that output has to be available, or for this register to work properly. Okay, what we need to add is that time for this register to act. That is from the leading edge of the clock to signal becomes available, plus this delay, plus this delay, plus header delay, and then setup time for this register here. Okay, so all these delays put together defines the critical path, and hence we can from this and you consider this for the whole microprocessor and look at the worst case delay, and based on that you can design the clock. All right, okay, so let's move to next part. Okay, what are the things that are required to execute an instruction, right? So most of these we have studied. Now we need memory. Okay, so without memory, a microprocessor will not work, right? Because registers are only few and registers keep temporary values. Okay, so memory is something where the whole program can reside. Okay, and then we can bring data from memory, and then we can store data into the memory. So the memory is very important part of the whole microprocessor system or processor system, without which it cannot function. Secondly, registers. Okay, registers are also required in our case because it, I mean, you can always design a microprocessor without a register, but it's not going to be efficient because registers are extremely fast. Okay, and then they help you also in a lot of other operations like addressing and instruction count and so on. So we have general purpose registers from X0 to X31. Then we have program counter. Then we have seen sign extender. Okay, that we have seen, right? How sign bit we can extend. Then we have to have ALU, which is add, subtract, and OR unit. And then we have add 4 unit that we have seen in case of, program counter has to be changed in every cycle to represent next instruction. And since we have 4 bytes as a length of instruction, so next instruction will be current value of PC plus 4. And compare unit, right? Or compare combination logic block. So these are the blocks that we have studied so far. We have seen adder. So adder here, in case of RISC-V, we will have 32-bit input. There are 2 inputs here, both are of 32-bit, and then when the output also of 32-bit, and then carry out. Okay, and there is also carry in. All right, so so this is very top level view of adder. Similarly, we have mux. We have 2 inputs in mux and 1 output, and then we have ALU. All right, so these are very simple diagram. Okay, and this represents only conceptual level operation, right? So in case of value, we have a 0 output. It means that when we are comparing 2 numbers and it's a 0, then this flag will be on. Okay, and also there is a control signal here which gives the operation, what operation we are executing. And these things we have seen in the last class. Okay, so this is what we have studied till yesterday. In today's class, we'll look at what are the storage elements. We'll relook at them again because we have already studied register file. Memory we have looked at in very brief. Okay, and then we will look at what is single cycle and multi-cycle machines. And then we'll start our design of the single cycle data path. Okay, any question up to this point? Are you there?
Yes, sir, we are here.
Okay, okay, thank you. And then we will look at implementation of one such instruction, that is add or subtract. Okay, so let's start with storage element, and I'm going very fast because you know all of this, right? So the memory here we assume is ideal memory. Okay, when we say ideal memory, it means that we are not looking at the operation, we are looking at uh, only at module level or box level. Okay, or black box level, right? I mean, so we don't we are not looking at the whether it has what kind of registers are there inside memory, like we have studied, memory address, uh, what do you call that, there are two registers, memory data register, etc., right? So we are not going to look at that. Okay, MAR and MDR, etc. So right now we assume that there is a bus here, which is input bus, or we can that, or data in bus, okay, which is of 32 bits, because we are assuming that in RISC-V all registers are 32-bit wide. Similarly, there is one bus which we call as data out bus, okay, which is also 32 bits wide. Okay, and then at the top we can see address. Okay, now this address gives the address of the memory. Obviously, this address will also be 32-bit wide. Okay, uh, so address gives the address of memory location inside, and size of this memory is 2^32. Okay, so now whatever the address value is available here, uh, whatever the address value is available here, corresponding memory location is read or write into. Now, if write enable signal is 0, okay, then whatever is the address here given by address bus, corresponding data will be available here. Okay, now we don't have to worry here about the clock signal. Okay, for reading can be done at any point in time as long as these address bits are available and write enable control is 0. Okay, when write enable is 1, whatever data is available into this data bus is returned into corresponding memory location whose address is given by this address bus, 32-bit address bus. Okay, is it clear? Okay, so I am repeating. For reading, okay, the memory works as a combination logic block. It means the read can be done at any point in time. Okay, writing can be done only at when the clock is going up. Okay, and at the same time write enable is 1. All right, then whatever data is available, data in bus will be written out here. Okay, all right. All right, so next is registers. We have already studied registers. So it's nothing but it's similar to D-type flip-flop. And then number of registers that we have in register file is 32. Okay, and data in is of, we have shown here n number of data in size is n, which is n bit input, and simply data out is n bit output. Right? So basically, for each register, right, in this file we have 32-bit input, and output is also 32 bits. So when we write into register, we are writing 32 bits and also reading 32 bits. Okay. All right. Okay. So basically, whatever data is available on 32 lines here or bus lines, that will be written or read. Okay. Now, there are some cases where you may have to, store say only 1 byte, etc. That's also possible, right? But in general, number of lines that goes into each register is 32. The similarly number of lines that goes out is also 32. All may or may not carry data all the time, right? All right. Or may carry 0 in case we are loading bytes, the remaining bits may be 0 or something like that. But nevertheless, we'll look at those cases later. Okay, so when write enable signal is negated or 0, then data out will not change. It means that whatever is inside, when write enable is 0, whatever is the value of the register inside will be available all the time. Only when this write enable is 1, right, then data out becomes data in after some delay. Okay, in the rising edge of the clock. Okay, so these points we have already discussed. This was just to repeat. So again, okay, all right. So now what we have been talking about essentially is about individual register. And now we can put all these registers. Okay, here we are assuming that is a single register. Okay, and we can combine these 32 registers and put them in a file, or we can say it's a register file, which is nothing but a block. Okay, these 32-bit registers inside. How they are placed, what is the design, that's not our position. Okay, and then we have one bus, okay, which is for writing. Note that although there are 32 registers, but we are doing writing only in one register at a time. So all the instructions you would have seen so far, you would have observed that writing is only into one register, while reading can be done from the two registers, right? So correspondingly, we have two buses called bus A and bus B, where the words or memory, or sorry, registers inside, two registers inside can be read at a time. Okay. Now, what are these registers that is to be read? That comes on to bus A. That address is given by this one, right? RA, control signals. Okay. Similarly, register B that is to be read. That those bits are available here. And then we are writing into a register. Okay, we can write only into one register. That address is given by the one here, right? That's RW. Okay. So basically, that's exactly what we have discussed in the points here, that there are register file consists of 32 registers, and each register, of course, is 32-bit. That's the reason we have 32-bit output buses. So there are two 32-bit output buses because we can read two registers at a time. And these two registers correspond to the addresses that are given here at the top, which is RA and RB. Okay. And similarly, we can write in a register, and that address is given by RW. And the data, when we are writing, then data should be available in bus W. Okay, simple. And when we are writing, then write enable has to be 1. Okay. Now, when write enable is 0, then we can read the contents of two registers whose values are given by, or whose address is given by RA and RB. There are 32 registers in RISC-V, and all 32 we don't need to show 32-bit register separately. We say that 32-bit register inside this register file, and this will have, and we can write one register at a time. So there has to be bus from which data can be taken. This obviously has to be 32-bit wide because each register is of 32-bit. So all the registers we are writing is of 32-bit byte. And the address of, now one of the registers we can write the value. Okay, so that register onto which we are writing is not fixed, right? So one of the 32-bit registers we can write, 32 registers we can write, and then hence that selection of that register is to this RW bus. Okay, and then we can read two registers at a time when write enable signal. Okay, so there is a control signal called write enable. When it is 0, then we can read the values from two registers. Corresponding addresses are given by two, RA and RB. Okay, I'm repeating, right? And then only at the rising edge of the clock we can do writing. Okay, so clock input is a factor only doing write operation, and read operation we can do at any point in time as long as write enable is 0. Okay, so this is now mapping of the registers, right? So we have two registers that we can read. The first register is specified by RS1 field. Second register that we have to read is by RS2 field. Okay, so these in instruction we have these fields, right? RS1, RS2, and so on, right? And RD. Okay, and then write register is, or destination register is specified RD. Okay. All right. And X0 we normally don't use because it's always 0. I mean, for writing. Okay. And then we have a program counter. So what we are discussing here is the state elements that we need. And then we have memory. Okay. Now memory we have said is the ideal memory. And this memory, now we know that instruction and data will be in the same memory. But for our convenience, okay, now we are assuming that instruction memory and data memory are separate. Okay, but they are part of the same large memory. Okay, so right now we are assuming they are separate because this concept will help us, to map reading and writing operations, or instruction and data, instruction memory and data memory to different caches. Okay, cache memories. Okay, which is instruction cache and data cache. Now, when we design, so basically the concept will be taken further for performance improvement by designing right caches. That's the reason they are showing instruction memory as separate as data memory. Okay, all right. Okay, any question up to this point?
Sir, actually, I had a question in the
yes, please.
Register writing and reading.
Register one?
Writing, reading, the slide before this.
Okay, all right, yeah.
So here, so essentially, the write enable will either be 0 or 1. And
yes.
In either case, it will either read or write. But what if you want to not do either? So if you want to retain the state of the registers.
So when it is 0, you will retain it. Only thing is that whether you use it or not, it doesn't matter. That's my understanding.
Okay.
Okay, you want to say that, let nothing be available at that point in time, just retain it. That's fine, you can do that. You can do that, but I don't know what design you will need and whether microprocessor really needs that. Okay. Normally, the idea is that as soon as, the whole design is based on the concept that values should be available at output as soon as possible, right? So there are 32 registers here, and we are taking data only corresponding to 2 registers here. Yeah, so you have a point here, so let me just get back to you on that, but I don't think there is some, these registers can be in a state where nothing is available. That's my understanding.
Okay.
Okay. Let me get back to you. It's a good question though, right? Very good question. Thank you. All right. So let's move into a single cycle and multi-cycle machine. Okay. So we have studied, remember lecture 8, we have looked at this single cycle versus multi-cycle machine. Now, so everything related to instruction happens in one cycle time. In case of single cycle machine, it means that whether it's a add instruction or add immediate or load word or store word or any other instruction, This has to happen in one cycle. Okay, so basically, sorry, it will be something like this. Okay, and in one cycle time, that this time, all phases of instruction execution must complete. Okay, so so here in the diagram we show single cycle one, wherein some instructions are going to take long time. Okay, while some other instructions are going to take short time, but we have to design clock cycle such that the most complex instruction or the instruction that takes maximum amount of time must finish in the clock cycle. Hence, there are some instruction does not reach such a big clock cycle. So you can see there is a free time available, right? Or we are not really doing it, running instruction at maximum possible speed, right? So what we can do is that instead of having a long clock cycle, we can reduce the clock cycles and let instruction take multiple clock cycles. Okay, so in this way, the overall we can finish number of instructions much faster, because let's say, for example, in the first case, first instruction takes this much of time, or rather this much of time. Second instruction takes almost like this time, and third instruction, so although it takes less time, but you'll have fourth instruction can start from this point onwards. So basically, in order to execute 3 instructions, you require this much of time. All right. Where in case of multi-cycle design, you can finish the instruction just in this time period. Okay, so we can schedule 4th instruction onwards, right? So the multi-cycle design or multi-cycle architectures are more efficient, although a little more complex in design. Okay. All right. So with this knowledge, we'll start designing of data path for single cycle. Okay. Okay. So this what we have discussed just now is repeated here in single cycle microarchitecture. Now note that what we are doing now is data path design comes under microarchitecture. Something or microarchitecture, as we discussed earlier, is nothing but implementation of instruction set ISA, right? So single cycle microarchitecture executes entire instruction in one cycle. Cycle time is limited by slowest instruction. This point also we have studied. It does not require any non-architectural state. Okay. Okay. It means that when we will see this point little later, that in case of pipeline design or multi-cycle design, we need additional registers and so on, right, for it to operate correctly. So right now in single cycle design, of course, we have state elements, okay, but these are part of architecture. So when we say non-architectural state, it means the additional registers, etc., that we don't need here, okay, in single cycle design. In multi-cycle design, each instruction is broken into smaller steps that we have seen in here, that there are multiple steps now, and each step can be done in one cycle. The cycle time is small. Okay, and then apart from this single cycle, multi-cycle, we have pipeline design. So this is the third which we will study at the end. Okay, so first we'll do single cycle design, then multi-cycle design, and then look at pipeline design. Okay, so let's start with single cycle data path, or which we call it one instruction per cycle data path. This is a more correct term. One instruction per cycle data path. Okay. All right. Before that, we will look at what RTL is, or register transfer language is. In fact, you would have looked at this much earlier, because sometimes in the beginning we have used this language, right, to describe an operation. Okay, but it's very simple. So syntax for this is given, and semantics is also available, right? So it's very well defined language. Okay. So for example, this instruction here is that PC man memory at location which is pointed by PC is nothing but an instruction, which has opcode field, RS1 field, RS2 field, RD field, and function tree field. Okay, so this is similarly you can have memory from memory location at location given by PC has this instruction which is opcode field of RS1, RS2, and immediate field. So immediate kind of instruction. Okay. And then, so we using this language, we can define various instructions. For example, add instruction we can define as RS1. So basically, register RS2's contents are added to register RS1, and then everything that's a result of this addition is moved into register RD. Okay. Similarly, PC is incremented by 4. So PC is incremented by 4, and then that becomes new value of PC. Similarly, we can define all these operations, right? It's very simple, and once you read this, it becomes very clear. For example, load word. Load word is what we are bringing from a memory location whose location is given by, or address is given as register RS1. Look at the contents of RS1. In that contains add immediate value after sign extension. Okay, so then this becomes the address, and from this address get the value and store into register RD, and then change the PC value by 4 to point to the next instruction. Okay, so this is very simple. Please go through it, and then you will understand. Otherwise, we'll read it from the book. It's available in all books. Any question? Okay, all right. So let's move ahead. So now we are going to look at only subset of this instruction set for discussion, right? Because if you look at everything, that may take a long time for us to design Datapath. So we look at very simple instructions: add, subtract, or immediate, load, store, and branch. Okay, and I'm sure you know what these formats are because we have repeated this several times. So we are not going to discuss now. Okay. So one instruction per cycle machine looks something like this. We have sequential logic, that is states or registers or memory, and then we have combination logic here. Okay, and combination logic output is available and goes to sequential state. All right. All right. So this is very simple. Okay, and then let's look at now at some details. Okay, so we have seen here that we have sequential logic for the state components, and what are these state components that we are going to use here is program counter, instruction memory, data memory, and register file. Okay, and then we connect this to combination logic, which could be arithmetic logic unit or adder or so on, right? Comparator and or maybe something else, right? And then we of course we have a loop here, right? I mean, because based on the output from combination logic, the state changes, right? So the state input becomes output of combination logic. All right, is it clear? Any question? Devyani, are you there?
Yes, sir. I think it's clear.
Devyani, you are able to understand it?
Yes, sir. I don't have any doubt.
All right, thank you. Okay. So now let's read this. So every tick of the clock, the computer executes one instruction. All right, it means that one cycle, one instruction is executed. Current state output drives the input of combination logic, okay, and whose output settles at the value of value of the state before next clock edge. All right, so the output here goes to combinational logic circuit, and then a combinational logic circuit does its work, and then output from this goes back to state elements and before next clock edge, and make sure that the value is stable when the next clock edge happens. So the value or output settles at the value. All right, and at the rising edge of the clock, all state elements are updated. Okay. Now, once this is done, then we move to the next cycle. That's all, right? So basically, we'll have to make sure that within one cycle, all the operation of instruction completes. All right. So of course, there is a clock connected to all these state elements. Okay. So this diagram shows the basic instruction execution. Okay. So now we can see at very gross level or top level view of instruction execution or data path. Okay. Of course, it's not complete because it is just very elementary diagram right now. So we can see the components here. We have program counter. Okay, and we have instruction memory, and we have data memory here. Okay, we have register file, and we have ALU, and we have one mux here. Okay, now why do we need mux here? Because program counter, value of program counter need not always be PC plus 4. So there is a, for instruction like branch and so on, which are or jump, okay, jump, JL, etc. We see the PC value is different, and the PC value has is value of the PC program counter has to be calculated by some calculations, right? Which is or some additions, etc. Right, or subtraction done by ALU. So we have to take one value out from there in case of those instruction execution, and then mux will be correspondingly enabled. So the control unit will enable the mux, and then PC value will be updated. All right. So that's one part, and of course there are. You can see this, output from register 1, register 2, and RD are going. Sorry, from instruction memory, we'll read instruction, and then corresponding fields will be read, and okay, and then there's a register file here. Okay, so of course from this we'll select the registers, etc. So we'll come to that little later, and then we have ALU. But something that's shown here is that it has 5 phases. First is instruction fetch. Second is decode, instruction decode. It makes sense of what instruction is, and then register read, or we are reading the register at the same time. Okay, it means that instruction, for example, it's A. Instruction is add, say register. Say I'm giving just hypothetically ABC. I mean actual register number could be very different. So basically, the register decoding is to be done by control unit, which is not shown here. It means that what this instruction mean to add corresponding what signals to be generated, and at the same time 2 registers are to be read. So it means that B and C will be read. Okay, so the output should be available in this phase. Okay, third is execute. It means that when B and C are available, we are going to execute. Okay, and then output will be available. And then fourth state is memory. Now there are some instructions like load and store, where output of this not really for add ABC. So say for example load word. Right, so effective address will be calculated, and then from data memory we get the word. Okay, so there is a memory phase where we write into memory or read into memory, and then we have last phase is register write. So register write, for example, if the output of ALU, in this case of add AB BC, the output that's available now can be written back to register. Okay. All right. Now this diagram is not really complete, so we'll not worry, why not the output here has gone to register, right? Wherein, so actually there has to be bypass here, and then it can go to register. So in next diagram we'll see that. Okay, so this is the timing, clock timing. It has become little dirty, so you can see that it's the time. Now this is simply represents uh, a clock. Note that when clock is high or rising edge or positive edge, we'll have to do all the writing into state elements. And the rest of the time, once we have done this, after some time, all the time is available for combinational logic circuit to do its job. Okay. Any question? All right. The question you may ask is that why 5 stages, right? Yeah, this is a good question. Now, many architectures have more than 5 stages or less than 5 stages, right? So this is how RISC architecture is designed. Okay. So if there is a possibility that in one stage, one stage is not executed. For example, memory may not be executed in add instruction or subtract instruction, right? So that's okay, but it simplifies the design. All right. Okay, where in some instruction use all 5 stages like load word or load byte. Okay, so now another 5 minutes. Let's see if we can complete the data path for add and subtract instruction. Okay, this is the add instruction, right? So you know it, right? So it looks something like this: add RD, RS1, RS2. Where is RS1, RS2 fields are here, RD field is there, and these 3 defines the instruction. Okay, or some sense opcode. Or so looking at this field, we can make out the semantics of the instruction. Okay, and then RTL corresponding to this is that contents of register RS1 are added to the contents of register RS2, and then result is stored in register RD, and PC is incremented by 4 temporal. And so, what are the stages here now? 5 states. First, fetch the instruction and increment the counter. Okay, the decode this as a add. It means that we'll have to decode it that and make out that is add instruction. And at the same time, we have to read register 1 and register 2. That's register X1 and X2 here in this case. Okay. And third stage is that execute these two, or execute this operation, that is add R1 and R2. Okay. Or contents of R1 and R2 are added. There's X1 is added to X2. Okay, and then in this instruction, we are not doing anything in memory because we are not storing the value to memory or reading from memory. So we are just writing it to register. So last phase is writing or WB, writing the result into register R3. Okay, which is X3 here. Okay, all right. Any question? Simple. Now this again is not a complete diagram, but it shows the flow. Okay, so in this case, okay, we are executing this instruction x3, x1 plus x2. Of course, this part of PC part, right? Increment of PC is being done here. Okay, instruction once from instruction memory, instruction is read and interpreted, or basically, I mean, is control signal will be generated corresponding to the instruction, and then there are x1 here, x1 address is taken out, x2 address is taken out, and then x3 address, or basically register 3 address is taken out, and then at the same time, corresponding to these two output registers are read, or 2 registers corresponding to 1 and 2 are read, and the values that are that will appear here, and then Then what is the next thing that will happen is that the addition will happen, okay, in this ALU. And then finally, in the last phase, now as soon as the addition happens, the value will be available here. And at the clock edge, it will be written into corresponding register RD. All right. So this is very simple. I mean, this at the top level, what we are doing here. Right? So let's look at the little more detailed design. So now we have shown here a control logic. Okay. And control logic can work based on what? It has to get the instruction and it has to interpret that. Okay. So from instruction memory, we are taking the instruction, which is 0 to 31. 0 to 31 is the complete instruction they are getting, right? And now in add, we have address A corresponding to register A or RA, okay, or register A. These bits are used to represent the bit 15 to 19. Okay, in the instruction, add instruction, right? Similarly, bit 20 to 24 represent address B, and then at destination register address is given by bit 7 to 11. So these corresponding field will go here. Okay, these bits will go to these ports. Okay. Now we'll have to see what will be the next here, right? Now this will be enabled. Okay, so this is register write enable signal that we have seen. Okay, in case of reading, then this will be 0. Okay. And then two values will be read from the register, right? So this will happen right in the first, or as soon as the values are available here. Okay. And then next thing is that these will be added, and then output will go to this register here. And at that time, when the value is available in corresponding last phase, this read write signal becomes 1, and so corresponding addition value, that is whatever value is available, will go inside register RD. Okay. So now this is a timing diagram. Okay. Okay. All right. So now if you look at that, now everything has to happen in very timely fashion, right? Because control signals ought to be generated at the right point in time. And then we can see from this timing diagram, right, what all will happen. Okay. So the clock is going here. Okay. Okay. All right. And then corresponding control signal are generated. Okay. And we can see the PC value, for example. Initial PC value is, for example, 1000. Okay, so this value is 1000. Let's assume that this represents the clock. Okay, and then after clock edge, okay, this is the which clock edge we are taking. For example, we are taking this clock edge. Okay, the next PC value becomes 1004. Okay, and then in this clock cycle, we are executing this instruction x1 at x1, x2, x3. Okay, and then we can see at this timing, register value R2 is read, and at the same time, register value R3 is read. Okay, and after some time, okay, there will be some delay, combination logic delay, and then this this addition will happen, and output value will be available here during this period. And then it will be, next phase is essentially it will be written into RD. Okay. And then now RD state is not shown here, but The output of ALU is shown here. So correspondingly, okay, correspondingly it will be returned to register RD. Okay, all right. So it's not what is register 1 shown here. RS1? No. All right. So maybe, okay, all right. I'm sorry. So register 1 here is actually RD, destination register, right? So what happens is that now this destination register will return only at this clock edge. Okay. So this value that's available here, register R, so summation of whatever we have read from here will now be returned into register RD. So RD value changes is available here now. Okay, is it becoming clear? What you need to do is that just look at each of these timing diagram. You just have at clock edge to draw one line and see what are the values and so on, right? And how combination. So between two clock edges, all combination logic will work, and you can see that how what are different values, and then how can you get the output. And only thing, remember that all these operations are happening before next clock edge. So here at the next clock edge, we have this result available, the summation of the two registers, right? This available. Okay. Shall we stop here? So we can similarly implement sub, and some here subtraction is exactly like addition. There is no difference, excepting that we can see that there is one more signal here which will control signal will tell ALU whether it's addition or subtraction. And based on this signal, whether it's 0 or 1, it will do for corresponding operation of addition or subtraction. All right. And so in this way, we can design all these instructions. All right. So that's all about the class. Right? So we have studied instruction set, requirement for instruction set, storage elements, the register file, and ideal memory, concept of single cycle versus multi-cycle data path, and we have seen the data path design for head and subject. Of course, in this class, we have not studied how control signals are generated, right? Which is nothing but very simple combination logic function. So that's we can easily design that. We'll look at that at the end. Actually, there are two ways of designing that control logic. Okay, any question?